My name is Alex Bulazel. I'm joined here with Jeremy Blackthorne. We're here to talk about Ghidra, NSA's reverse engineering tool, which was released about a month ago. GitHub link at the bottom includes some scripts you can look at, as well as some binaries you can reverse with Ghidra. As we said, don't worry if you don't have a laptop. If you do, you can follow along. If not, we're going to do everything live up here on stage. A little disclaimer before we get started. No classified information in this talk. We're also not here representing NSA or the US government. We're just two private citizens, big fans of the tool, and working off the publicly released tool that's available on GitHub to the whole world. A little about me before we get started. I am a senior security researcher at Riverloop Security. You may have seen me on the conference circuit over the past 2 or 3 years. I've done a number of presentations internationally, primarily focused on reverse engineering consumer antivirus products, most recently Windows Defender. I've also done academic publications at Usenix Woot, as well as Roots, and recently published cyber policy with Dave in Lawfare. Worked with Jeremy at RPI, at Lincoln Lab, and at his company BCI. And I also want to say I'm a very proud RPI Sec alumnus. I know a whole bunch of RPI guys are here in the audience, guys and girls. And that's about it for me. I'm going to come back in the second half and walk you through scripting and interactive use of Ghidra. Jeremy's going to take it away.
Okay. Hello, everyone. My name is Jeremy Blackthorne. I'm an instructor at the Boston Cybernetics Institute. It's a fairly new company. We do training in reversing, vulnerability assessment, exploitation of embedded systems. So all the stuff why we come to Infiltrate. That's what we hope to do is train and make more people like you. I'm a PhD candidate at RPI. My thesis is focused on environmental keying, taking it to the next level. I'm a former researcher of Lincoln Laboratory, spent a few years there. And I also had the pleasure of serving in the United States Marine Corps 2002 to 2006. Any Marines here today? Hoorah. I am also an alumnus of RPI Sec. Okay. If you are participating, which I don't know how many you are, based on the whole, do you have a laptop or not? Simple steps, just gotta have JDK11, download the Ghidra, from the website, and a couple of our demos and binaries. Like Alex said, if you don't have a laptop, we'll still try to keep you entertained up here, okay? Okay, so what is Ghidra? First of all, it's a Java-based reverse engineering tool, so that has huge advantages for cross-platform, compatibility and everything. It is made by the NSA. Right now, it is static only. Although Rob Joyce has said that he is they are gonna release some debugging functionality, additional functionality to come, basically. At the bottom of the screen there, you can see a little screenshot. It's kind of interesting. If you grep the source code, you'll see that some dates pop out, and they're not easily attributed to like standard imported libraries or anything. So it gives us some basis of maybe how old the tool is. I was just thinking of the timeline in Windows Keynote today, where she showed each major event. I'm thinking maybe we can put Ghidra in there now as one of those major events of, at least started coding back then. Okay, so explaining what Ghidra is kind of sucks, right? You got to just see what it is. So let's take a look. So if you have Ghidra installed, just go ahead and start it up. Okay. So Ghidra thinks this is the first time it's ever been started on this computer, so it's asking me for licensing agreement. We're just going to click through some of these things. Okay. Tip of the day, some help, things like that. Okay. So we're at this prompt now where it's like, when do we get to the fun stuff? It kind of reminds me of Visual Studio when I first started using it. It's like you have to do 7 steps before you finally get to see a single print statement. So that's what we're gonna have to do. We're gonna go through these. So if you got Ghidra open, let's make a new project. We're gonna do non-shared as opposed to shared. Ghidra does have some synchronization capability. You can do like a git push pull and set up a Ghidra server. I'm not gonna cover that. Alex might talk about that later. So let's just make, let's see, make debug 2. All right. So I have a project made finally, but I don't have any binaries in this project. So what we're gonna have to do is we're gonna have to import files into this project. And so you can go to File, Import File, or you can use hotkey I, whatever you want. And what I'm gonna do is go to our Infiltrate GitHub, and we have 3 binaries in there. We got a Mako, PE, and ELF. So if you wanna, whatever system you're on, you can run it. I'm just gonna pick the ELF here. Okay. So it gives you some, it recognizes some basic information about it, okay? All right, so it's giving me basic metadata, you know, file attributes, things like that. We're getting closer to finally seeing what this, what's the hype's all about. So now, finally, I get to double click this executable and it's gonna open up this tool right here. So Ghidra projects can have multiple tools in them, and you have a tool chest. Up here, it only came with 2 of them. There's the code browser and then some version control. And the code browser is what you think of when you think of Ghidra and reversing or IDA or Binary Ninja. It's like, it's the code browser, right? So let's double click this. Love that animation. Okay. Has not been analyzed, let's say yes. And here's a list of just a lot of the default analyses that come with Ghidra. Of course, you can write your own and integrate it. Or you can uncheck these if you know you don't need them for efficiency purposes or what have you. So, okay, analyze. Okay, finally, we're at this tool that we've been hearing about for so long. People have written songs about this. I think he's here today, right? Yeah, Brennan Phelps, yeah. So people wrote songs. There's like so much hype around this tool, right? So what are we looking at here? So I'm going to orient you to what we're seeing. So the main window here, like right in the middle where you see all this information, this is just going to be your disassembly. So you think this is like your text-based code listing in other tools you're familiar with. On the left side, you'll have program tree, which is just, it gives you all the different segments of the program. Then you have a symbol tree and imports, exports, functions, things like that. You have data type manager down here. So let's get to something a little bit more familiar. So let's just jump into a function. So if we expand functions down here, scroll down, we have symbols. So just click on main, and that's kind of the hype right there. Is on the right side is we now have decompiled code from an open source free tool, and the decompilation is not perfect, but I can say that it is very useful. Okay. So on the left side, we got disassembly. On the right side, we have decompilation. It's really small, I know that. So one of the first things I'm gonna do, I'm gonna settle into here to my tool. I'm gonna start nesting, you know, like start making things I wanna make it look like the way I want it to look like. Okay, so under decompile window, I'm gonna change the font size. Let's go here. And okay, so a little better. And changing the font size is just like you'd expect from any tool to be able to do that. But one of the strengths of Ghidra is its ability to customize every last little thing you can think of. I mean, it is open source, so at the very bottom you could fork it and then rewrite whatever you want. But built into it, you can make your own changes and kind of tailor it to you. So let's look at the left side here of this main function. And right now it looks kind of ugly. So we have addresses, then we have you know, bytes and hex, then we have the opcode, operands, but look at the way that it's all laid out. It's kind of like jacked up, like it's word wrapped or whatever. So okay, so I don't like this, right? So let's change that. So at the top here, you'll see this in a lot of windows. You'll see it repeatedly. There's this little thing like a brick wall right here. And what you can do is if you click on this brick wall, you have the ability to customize everything about the display that you want. So in this case, the way it's displaying the hex bytes is kind of annoying to me. So I see where it says bytes, and I grab this slider, and I just move it over a little bit. Now I have, you know, something a little bit more sensible. This is what I would expect, right? But I know in other tools, you know, you can make customizations, but I just found with this one, I can make more customizations than I'd ever want in this tool, but I'm sure there'll be people out there that, you know, it's never enough. They want to keep customizing. So one of the things I wanted to highlight right here while we're in this view is the P code. So the P code is one of the, you know, secret sauces of Ghidra right now. And Alex is going to talk a little bit more about it, but since I'm in this view, I want to show you. One of the things you can do right in the disassembly listing is you can enable and disable fields, and so I'm going to enable P code. So we'll see, what is this P code all about? Let's check it out. So enable field, and then let me get out of that view. Okay. And then what we see here is how Ghidra is parsing each one of these assembly instructions in this intermediate language. And P code is going to play a role, like I said, Alex will talk more about it, but P code plays a role in how you translate from one language to another, from assembly to decompiled pseudocode, or from hex to assembly, things like that. For me, just in the purpose of this demo right now, showing this P code is not very practical, but I just wanted to let you know it's there. Okay, so let's disable field. All right. Now, the name of the talk, Ghidra, the mastering with a 3. There's a 3 in it somewhere, right? So, what's the third head of Ghidra? Well, I mean, I don't know. They didn't have a press release that said, here are the 3 heads of Ghidra, but if I had to guess, I would say, here's probably the third one. So you have the text listing view, you have the decompiled view, and then you have here the graphical view. So like, your control flow graph. And when I talked about all the different customizations, you see here in the control flow graph, my bytes are cut off, with the ellipsis showing here. In my control flow graph, I don't really like seeing the bytes. That's just left over from my habits from other tools. So I'm going to go in here. I click the brick wall icon there, and I'm just going to disable addresses. And now I don't have the addresses anymore, right? And you can just keep doing that over and over. You'll just keep finding that throughout the tool, that if you like something, you can go track down pretty quickly how you can tailor it to you. And so just as a, kind of a forecast on my part, what I think is going to happen is, we're going to see Ghidra tailored more and more to all of its different purposes. Like you have different distros of Linux that kind of specialize. You might see different distros of Ghidra. Like you'll have an embedded one that's set up for all embedded stuff. You'll have one set up for all Windows and hotkeys and whatever, things like that. So just a, short prognostication there. Okay, so now I have this window. It's floating around and it's annoying. And so what I need to do is I need to dock it. And that's one of the other great things about Ghidra. Muscle memory there, sorry. I'll spit out Binary Ninja later, I'm sure of it too. So I'll just grab the blue bar here, and you can grab any blue bar you see anywhere in Ghidra, and you can just drop it into another one, and now it's tabbed. But maybe you don't like it tabbed, so you can grab the blue bar, and you can drag it all the way to the right. You see a little arrow appears. That's pretty difficult to see. I'm gonna see if I can get a zoom going. Yeah, there we go, see? Little arrow appears. And when the arrow appears, it's like you're docking it over there. So let me see, I can do this again. Yeah, there we go. So you can dock whatever you want, wherever you need it at any time. And Ghidra will save your settings. So when you close Ghidra, open back up, all of your stuff will still be there. Okay, so let me throw this back over here. Okay, I want to share this feature that somebody showed me yesterday who has specifically requested to remain nameless. But to open up these different windows, sometimes I don't know where the window is, right? So I want to open up. So I hit the decompiled button up here, which is like this C, display decompiler. And so I click it. It's like, okay, I display it. And then I'm like, where is this? I don't know where it is. I click it again. I'm like, no, where is it? I click it again. And then it starts getting angry. I don't know if anybody knows about that yet. I have not seen anyone talk about it. But if you keep clicking it, like it gets, like I really want to know the developer that was like, showed that to somebody. Be like, I know you had trouble finding the window for the umpteenth time, so I put in a feature for you. And now it'll just pop right out at you. So whoever that is, please, I want to chat with you. Okay. So we dig in a little bit more. Let's see. So we see that it's a lot of different features, helps you parse code. One of the things that I'm going to want to do as a reverse engineer is, say like, I'm just going through this binary. I want to hunt down and see what this binary does. I see the names of the functions here. Pass 1, pass 2, things like that. Let's see, I can run this thing too. Let's see. Okay. Real exciting, right? Paid a designer to make that ASCII art for us. So just ask for a couple passwords, and then there's another thing in there too. So that's what we're looking at. So if I wanted to reverse engineer this, I want to get an idea of how is this program laid out. So A lot of times when I'm training new reverse engineers, they just like jump right in, they start reading the assembly line by line. I'm like, no, you need a bigger picture, right? So start at the top, go top down, breadth first, if you're just trying to get familiar with the binary. So up here under program trees, what I can do is I can right click here and go modularize by, and then complexity depth, dominance, subroutine, a lot of different options here. I do dominance, let's see dominance. And then scroll down a little bit. You'll see this pop up, this little directory here. What I'm gonna do, I'm gonna right click up here, expand all. And then what we see here is it's ordered functions. You know, here's main, and then within main, here's the functions main calls. So it was just a nice little feature. I mean, you can also do complexity depth, but the real reason I wanted to show you that, not because that's like a big wow feature, but really what I wanted to show you was its help functionality. So to me, that was one of the biggest things that stand out, especially as a teacher, is empowering students to help themselves rather than, you know, coming to me for things. So the help feature of this, so I'm in the menu here, and I'm on dominance, right? I didn't explain what dominance is. So what I'm gonna do is I'm gonna do F1 while I'm in the menu tree there. I hit F1, and what comes up is Ghidra's context-sensitive help menu system. So wherever you are in Ghidra, it doesn't matter what you're clicking on, that feature is linked to basically what is an article that explains exactly what it does. So when people, the refrain sometimes in my classroom is like, you know, what does this command do? I'm like, there's this one command that will tell you, and this is called the man page. So type man. And now in Ghidra, it's going to be, did you try F1? You do F1 first, then you come to me, and then we'll talk about it. So, but, you know, if you're starting out, that's, you know, and everybody's starting out with Ghidra, right? Or a lot of people are. So, okay. So if we check out, let's say pass one, I'm just going to double click into pass one, takes me into pass one. And then, okay, what is this? So it has all the basic features you'd expect of any code browser. So it's got manipulation and navigation, things like that. So here I see, okay, it's a printf, scanf, string compare. Okay, scanf, local 24. Okay, so this is taking my input and then it's either saying congratulations or nothing. So what is it going to be? This is going to be user input. So I'm going to right click and rename variable. And for those of you who've been reversing for a while, all of the hotkeys are going the wrong way. They're abrasive to my psyche, because instead of like what you may be used to, they are sometimes the opposite. And so one of the things I've done is I've taken the key bindings, 20 of the most commonly used key bindings in IDA Pro, and I've mapped them into Ghidra. So that's available on my GitHub, there's a link or whatever. So it's like it's like 2 steps, you just click to import it or whatever. So let's do rename variable. Let's go user input. Okay, let's see down here. Okay, what is this? Okay, this is probably a format string, so I double click, and then it's going to take me over here, and we see that it's a string, but Ghidra didn't recognize it as a string, so it's not perfect, right? So what are we going to do? Well, we're going to tell it to format it as a terminated C string, okay? And then we see the decompiled code has now updated to the terminated C string, and let's see, what else we got left here? String compare, ivar, so we'll name that to status flag, whatever. And there you go. You know, you got your reverse engineered, reverse engineered function. So, okay, let's say status flag was a terrible name for a variable. Here's one of the other, I guess, big features that people seem to care about in Ghidra, which is the undo button. So there's an undo button. I don't know if some people, you know, they have the IDA Pro no undo, no mercy. I've seen those shirts around. So, or no surrender, yeah. Which it's hard to let go of that. You know, so, okay, but you got it. So I'm going to do Command Z here, and I hit Command Z, it goes back. Ta-da, right? It's like, yeah. So, NSA, that round of applause is for you and your undo button. Okay. So another thing I'll show here, is one of the last things I'll probably show, is if I go to, because that function was like, you know, really lame. If we go to the next password function, we see here, this one is a little bit, it's a little bit more involved, right? A couple things I wanted to tell you here. So for one thing, Ghidra is pretty aggressive in its analysis in both the assembly and the decompiled code, and sometimes it's too aggressive for me. As in, I want you to show me what's there. Don't tell me what you think I should see and not see. So like for example, if I right-click in the decompiled view and I go to properties, let's see, and then I go up here, decompiler analysis, eliminate unreachable code. So a lot of times, like Ghidra does not understand there's a buffer overflow where this code section was. And so it's like, oh, it'll never reach that. You don't need to see that. And I was like, no, Ghidra, for real. What are you doing? Stop doing that. So, but one of the things I want to do here is just in the display, I'm going to clean it up a little bit, and I'm going to remove the typecasts. So these typecasts are kind of like, I don't know, a little verbose for me. So I'm going to disable printing a typecast, apply, clean it up a little bit. Okay. And then the rest of it is kind of like, you know, you can name the variables and the string formatter, you know, specifier, all those types of things. But one of the good things here about having that P code in the background and that powerful system of understanding and intermediate language is it has other features built in from program analysis. So right here, let's take a look at a variable like, let's say scanf. So scanf is, you know, this is my user input here, like that. And I want to know where my user input is being used after this, which, you know, we've had to do in our head for a long time. But now with much better programming analysis tools. So what we can do is, let's see. Actually, let me grab Sterling of, actually, I don't know what that one is. There we go. Let me grab this one here. So Ghidra is definitely not perfect, and I've had some unpredictable behavior on this, so I'm still learning it. I can't say whether it's the tool or whether it's me. It's likely me. But let me grab this variable here. So it just says length, and what it's going to allow you to do because of the P code is you can highlight forward uses of it via the variable being modified or instruction lines that are referencing the variable. So it has some program analysis stuff built in, but it's really just a basic feature, right? Like, let me see here. So I right click there, let's do highlight forward slice, and okay, it highlights it there. But what I wanted to do was down here where it says user input, I wasn't even getting the context menu, and I don't know why. So I'll have to figure that out. So let's see. You mean because it's a global?
You named it twice as external. So in task 1, you named user input.
Let me try user input 2. Yeah, so I'm still not getting the, so I'll figure it out, you know. But, so if there's a vibrant community around Ghidra that's like, you know, having fun with it and tweeting all these kind of new cool features or whatever, this is kind of one of the times that if you're like, I don't know, I'm kind of new at this, it's like, well, actually the majority of the population is still new at this. So you can just jump right in now and, you know, start playing with it, integrate it with your workflow with other tools like Binary Ninja or IDA Pro or GDB or, you know, whatever you're using. This is like plays a part in it, you know. It's good? Good on time there? Okay. Okay, so that was just like basic, let's get familiar. And now Alex is going to take over, and he's going to kind of take us from walking to running and kind of show you what this thing can really do. Okay?
Thanks, Jeremy. So I'm going to take over and show you some of the features that Ghidra has for automation, for scripting, for program analysis, and, you know, beyond the basic usage, beyond just clicking and editing variables and so forth. And before I do that, I do want to note big thanks to Dave Itel for making the Ghidra tattoos. Put it on. It's in your swag bag, so maybe you'll see some at the dinner tonight. I really wanted him to make those and harassed him until he did. All right, so I'm going to talk about scripting Ghidra first and do some interactive demos of the scripting capabilities built into the tool. First off, a few slides. Scripting with Ghidra is available natively through Java. As we said, the tool is implemented in Java. It's also available through Python, which runs in Jython, basically Java hosted, or rather Python hosted in the JVM. Scripts can be run interactively in the GUI, so actually while you're interacting with the code, you can go up to the script menu, choose to run a script. And they can also be run in headless mode, so automatically sort of on the command line or in a batch processing context. It comes with, I think, currently 238 scripts already included with it. And these include simple educational examples, things for code patching, importing and exporting custom binary formats, and then also a variety of analysis enhancements. In particular, I was very impressed with the VxWorks analysis enhancements that are included with the tool. And it did seem like, I think the first release of Ghidra had around 230 scripts, and the latest one is 238. They seem to be pushing more scripts with the subsequent versions that they're releasing. In terms of Ghidra's APIs, there's really two APIs, or maybe one API that's a subset of the other. The flat program API is the simple subset of the API that's stable, version stable, cross versions. And it provides simple access for common things you want to do while reversing. So iterating, modifying, querying, creating, deleting various structures, functions, data, instructions, comments, so forth. This is akin to, say, like the simple idlepython API, where you're not digging in deep. Really easy to use and fast. It's also generally not very much object-oriented, whereas the rest of the Ghidra API is very heavily object-oriented. So you have a function object, an instruction object, a P-code op object, and so forth. With the API that is more object-oriented, it's very large, it's very well documented, but it can be intimidating. Lots of functions that take 7 or 8 parameters, and those parameters are, in fact, other objects and things like that as well. I wanted to highlight some of the features of this API. First off, Ghidra comes kind of batteries included with a number of interfaces for doing common things you do while reversing, interacting with P-code, programmatically interacting with the Ghidra decompiler, parsing C headers and C files. Cyclomatic complexity is one demo I'm going to show. Built-in features for calculating cyclomatic complexity. You don't have to do graph traversals yourself. Now, in addition to those reversing specific features that are included with the tool, a number of utilities for doing common things that you just might want to do while manipulating data. So serializing and unserializing different data formats, interacting with XML, doing hashing of different buffers of data, things like that. This is really nice because these are tasks that you might sometimes go and want to get, like, say, an external library to do. And if you were building a script in another tool and the tool didn't have those included, you might end up, importing some library. And this could cause distribution and compatibility problems if you're distributing across different platforms and so forth.
Let me swap you because you're cutting out.
Thank you. Cool. There's also built-in Eclipse integration for Ghidra with the Ghidra Dev Eclipse plugin. I will say it takes 10 or 15 minutes to get set up. So if you're following along live, recommend you don't use it right now. But it is really nice that, very strong integration with Eclipse for writing Ghidra scripts. All right, so that covers the intro to scripting. Now I'm going to move into showing you a couple of scripting demos. First up, Hello World. So we're going to go over to Ghidra here, same view that we left off with Jeremy. And I'm going to zoom in on this green plus button at the top to open the scripting window. So let's click that. And up here we see our script manager. The 240 scripts are all here. We can scroll through them, read what they do. Check them out when you're at home. These are all included, built in with Ghidra. But I'm going to go up here to the scroll and create a new script. Let's choose Java. Let's call it Hello World. And now we get a window over here. I'm going to make this font a little bit larger so you can see. And this is Ghidra's built-in script editor. It's not very nice. No syntax highlighting, no auto-indentation, no tabs, anything like that. But it is nice that you can edit scripts right in Ghidra itself. You don't have to have an IDE or even open another external app to do so. So first thing we want to do when we ever create a new program, new language, new environment, we want to say Hello World. Let's save that. Go back over here to Ghidra. We're going to go to our script manager, and then I'm going to click this green play button up here at the top of the script manager. Now you'll see down here in the console window, it prints out Hello World. Didn't get a new line in there, so it just prints out right into the next line. But there you go, Hello World. I'm going to move this over here so you can get a better view as well. And let's do something a little more interesting with it. I'm now going to iterate through all the functions of the program and print out their names. So we're going to grab the first function in the binary, and then we're going to iterate over all the rest of the functions and print their names out. Save that. And again, hit this green play button at the top in order to run the script. And now we ran it, and we see out here in the console window, it's printed out all the names of these functions. These names are also automatically clickable, as well as any address you may print out is clickable, and it'll take you right to that function. As you can see here, just clicking through, we're brought to the functions. So that was a quick hello world in Java. Let's also show off the Python API. So I'm going to do the same steps. Click the new script button, choose Python. Let's call this helloworld.py. And Ghidra sometimes has a bug where you will not be able to click into an editable buffer. So I'm just going to reopen this window. There we go. Save this, and now we can run it. You'll see this chomping red dragon for a second. That's the monitor. It's basically kind of Ghidra's form of the beach ball of death or the turning hourglass. It's telling you something's going on in the background. It needs to crunch some numbers and do some stuff before it can give you control again. So booting up the Python interpreter does take a second. So that ran, and now we've printed out those values again here in the console. We can also clear the console by hitting this little eraser button up here at the top. So I'm going to clear the console, run that again for you, and it'll be faster now that we've booted up the Python interpreter. You'll also notice with this script, I just did printf. I didn't do any format strings or anything like that, or f.getName. That's because Ghidra's Python API includes a really nice two-string implementations when we ever interact with a object as a string. So that was the basics, the 101s, the hello worlds. Let's go into some more advanced scripting. I'm going to go up here to the script directory button, the bullet points, hit the green plus, and I'm going to import our Ghidra 2019 directory that you can find on GitHub. Click dismiss, and now we go over here to the Infiltrate tab, and you see we have a few more scripts available. Let's start with the crypto constant search script. And actually, I have that one open here in Sublime Text in another window. So this script is going to search through a binary and find instances of particular crypto constants. In this case, we're looking for MD5 constants, and just going to tell you where they're found. You can imagine this being a common task if you're trying to identify, say, a library linked into a piece of firmware. Maybe you're trying to triage some malware, or just get a feel for a binary. You want to know where and when it's referencing different crypto constants. So obviously, there are already scripts you can do this with IDA and so forth. This is a simple toy version of that script for Ghidra. Basically, we have our array of scripts. We're going to iterate through that array and then find all occurrences of those addresses in a program, return an array of addresses, and then print out some information about them. I wanted to show you how easy it is to use the Ghidra API, so I'm just going to start with some live coding. We need to actually first find the first occurrence of a byte sequence in a program, so I'm going to use the memory.findBytes API. I basically have a handle to the process or the program's memory space, the base address, and so forth, and we can tell Ghidra to search through that memory range and find these crypto constants. You'll also notice here the converter object. This is a endianness conversion object that I've prepared. So something built into Ghidra. You can imagine working with endiannesses of different architectures. You might be needing to frequently change the endianness of a particular data buffer you have. So Ghidra includes capabilities to do that for you automatically or built into the tool. You don't have to write it yourself or include any external libraries. So in this case, we're going to respect the endianness of the binary that we're looking at and convert the sequence of bytes to the appropriate endianness before we search for it. So given all of that, I need to populate this address object for the first occurrence of the byte sequence. So what you'll see with this API, we pass in the base address to begin looking for the sequence of bytes at. We pass in the actual byte sequence in the correct endian order. Null is for the mask. You could specify a mask over the sequence of bytes. True, we want to search forward through the program. And then get monitor is basically a handle to that monitor object, to the chomping red dragon or to the hourglass you sometimes see in the bottom corner of Ghidra. That's giving a handle to Ghidra that it can render that dragon if it needs to, if something is taking a little too long, and let the user know that it's running in the background there. Now that that's populated, our loop will work, and you'll see after we find a particular byte sequence, we're going to search again and try to see if we can find that sequence again in the program. Let's save this. Go back over to Ghidra, and now run this script again by hitting the green plus button up here, green play button. And you'll see it says now we've found these crypto constants at these particular addresses. And these are also clickable in the same way the function names are clickable to take us immediately to those addresses. You'll see, so the first one is actually in a function, but then the second occurrence is over here in some global memory. So it's like a global variable. But you'll see here all the parentheses say NA after the constant is found. Let's change that. So going back to our script, after we find all the addresses, we're going to iterate over them and see if we can get the current function that's at that address. So you'll see here now I've used the get function containing API to retrieve the function containing that particular address, and then with the function object .getName in order to retrieve its name. Saving this and going back over to Ghidra. Let's clear the console window and run the script again. Now we have filled in that data, and for the uses of these MD5 constants in a function, we actually print out the function name in parentheses, as well as the addresses. You'll also notice that was pretty simple to do. We just pass in a single address and get the function containing it. This is an example of the simple Ghidra flat API. Easy to work with, easy to use, not very heavily object-oriented. There are other APIs, like the memory find bytes, where we've got to pass in 7 or 8 different arguments. The flat API is much simpler. Single argument, and we're done. I want to show you another script after that one, doing something a little more advanced and showing some of the more built-in capabilities for more advanced analyses that Ghidra just automatically includes that many other scripts would have you have to write on your own. So if any of you are familiar with cyclomatic complexity, it is a measure of a given function's complexity, and rather that means the number of paths that can be traversed through the function, so from entry point to exit. It's a useful metric you might want to know if you were, for example, looking to fuzz a program and you wanted to find a complex parsing routine or a function that has a lot of state contained, a complex state machine implemented in that function. Knowing that the function has a high cyclomatic complexity will tell you that it's complex and maybe bugs lie there. So I built a script that will go through a program and find the cyclomatic complexity of each function in the program. And it's called compute cyclomatic complexity for all functions. And it's actually really easy to do this. I don't have to do any graph traversal, don't have to work with any basic blocks at all. I just iterate over the functions in the program, and for each function, I ask Ghidra to calculate the cyclomatic complexity for me. There's this object called cyclo, which is a cyclomatic complexity object. It just said cyclomatic complexity cyclo equals new cyclomatic complexity, and I got this handle cyclomatic complexity object. Then basically I iterate through each function of the program. I use the function manager to do that. And I'm going to create this object, basically, func_cyclodata. And in this object, I'm going to take a function, get its entry point, and then calculate its cyclomatic complexity, again, using Ghidra's built-in features. You'll see here, again, the call to get monitor. Obviously, traversing through a graph could take some time, so Ghidra wants to have that monitor so it can alert the user if it's crunching numbers in the background. This object basically implements addressable row object, so it works with Ghidra's UI features in order to render an interactive UI window, and all we have to do to make that work is just implement the appropriate class, the addressable row object. And here's some more stuff just for configuring that UI window. Let's go to Ghidra and run that script. So this is compute cyclomatic complexity for all functions. Hit that green play button. And you'll see now we get a pop-up window with function cyclomatic complexity. So you'll see here we have a listing of each function, its address, name, and then cyclomatic complexity as computed by Ghidra for us. This is sortable, so we can sort by maximum cyclomatic complexity, sort by function name, sort by address. It's also right now configured that when we click on a function, we'll be taken directly to it. So let's look at this high cyclomatic complexity function for MD5. We go over here. I will pull up that graph view again. And you can see this is a number of basic blocks. And according to Ghidra, there's 10 ways to traverse through this function, cyclomatic complexity of 10. A simpler function like strlen, in this case, it's just an imported function. So it's a cyclomatic complexity of 1, single way to get through this function, just from the start to the end. Now, that's interactive mode. Let's say I'm reversing the program live. I might want to run that. But what if we had a number of binaries to triage, and we wanted to calculate cyclomatic complexity over all of them? You could run Ghidra in headless mode in that case. I'm going to go over to my terminal. And here I'm going to run headless.sh. Ghidra has kind of a complex format for the arguments it takes on the command line, so prepared a shell script that sets it up for me. But basically, we're going to run Ghidra's analyze headless script, pass in some parameters. We have a Ghidra project already prepared, and we're going to tell it, for each program in this project, run our cyclomatic complexity script. In this case, we only have one program in the project, but you can imagine you could include a number, you could initialize with a number of programs, and then run a script over all of them. So I'm going to hit enter. Get some Java boot up information. And here we go. We've printed out the cyclomatic complexity of all the functions in this binary. In this case, this is actually bin ls. This is not the same binary. It's just showing you an interactive mode. And scrolling up here to the top, we have some functions of high cyclomatic complexity, such as this one with a complexity of 75. Here, one with 50. And then a number of imported functions that just have a cyclomatic complexity of 0. Again, this is a simple demo, but you can imagine with these capabilities to run this in headless mode automatically, you could do all kinds of interesting things. You could expose this through, say, a web service, like an RPC type thing, and you could send some binaries over and get the results automatically. Implement this in, say, a web server and serve up information to a user who's uploading a binary. You could run over a number of programs and export data into a database or over a socket. All kinds of things you can do with this powerful headless mode. And also, I wanted to show you one final thing with the Python scripting capabilities. I've here prepared a script that will let us XOR some memory. Again, a common task probably during CTFs and things like that. And I wanted to show you what it's like to work with the Python API. I'll talk later about my opinions, Java versus Python. Personally, I prefer scripting in Java, actually. But to give you an idea of what the Python API is like, here's some code we can kind of fill in the blank with and iterate through a number of addresses that the user has highlighted and then XOR the memory values there. So let's first just iterate through a region of memory that a user has highlighted and print the addresses contained in that memory. So this script will only work actually on memory that's not defined yet. So we're going to go over here and run this XOR memory script. And you see I've highlighted with my mouse a region of memory. Click that play button. Syntax error. Hit that play button again. Oh, whoops, typo. And there we go. We've printed out our program selection, all the bytes that we've selected. And I can click these and be brought to that range. So now let's, for each byte in that range, retrieve the byte, XOR it with a value, and then set the byte back to that value. Here again, using the simple Ghidra flat API. Oh, good point. Thanks. Using that simple API, we can retrieve a byte and set the byte back at a given address. Let's run it now, and we're going to XOR all those bytes with 41. And you'll see there, they've been XORed with 41. And we can go back and de-XOR them, and so forth. We can choose this buffer. I think this one's actually XORed with 42. And it'll display a message. So that's a taste of the Python API. You'll notice here, I end up using basically these Java APIs through Python. It's great for very simple scripts like this. I think it tends to fall apart with more complex scripting, as I'll talk through later. So that was a taste of scripting with Ghidra. Now I want to talk some more about the P-code and SLAY and the program analysis features built into the tool. So P-code is Ghidra's intermediate representation, intermediate language. So this is obviously a very hot topic right now. Big credit to the guys who developed Binary Ninja for pushing ILs as a tool for reverse engineering and program analysis. We had other energy as well. People like Trail of Bits doing Mixema recently. There's been a lot of excitement about ILs for reversing and program analysis recently. Ghidra's ILP code seems to date back to at least 2005, according to the documentation included with Ghidra. And P-code provides basically a common interface or a common language for lifting code from a variety of architectures to this common P-code interface, where it can be analyzed for data flow, as well as decompiled. And it also enables users to write scripts interacting with the P-code and do analysis in a platform-agnostic way, while also abstracting away some of the complexity of these complex CPU architectures. P-code is a pseudo-assembly, so it represents lifted instructions as a small atomic operations without side effects. So side effects are made explicit. So if an addition will set a register or assign a flag register, they will break it up into the addition, and then they'll check the results of the addition and then set the register appropriately. There's no side effects for each micro-instruction. P-code also includes built-in floating point support, which is something that not a lot of program analysis frameworks necessarily support out of the box. It's a more complex thing to model, so it's impressive that they have that pretty seamlessly included. Again, you'll see here some examples of some raw P-code. This is the P-code for move XD racks, EDX, and here for an LEA instruction, as Jeremy showed you earlier with the graph view. A bit on P-code's design. This is quoted directly from NSA's documentation included with Ghidra about some of the design decisions they made with P-code, as well as some of the language around P-code. So RAM translates to a P-code address space. Registers are represented as var nodes. Var nodes also represent local stack and heap variables or global variables. All kind of data that you want to interact with the program is abstracted away as a var node. And then instructions are abstracted away to P-code operations. Here's another example of some P-code with a complex instruction, scasni repb. So you have a prefix on here, repeat this instruction. And this is a one-to-many translation, where this one instruction translates into, 15 or more P-code operations. Brief overview of P-code. This is not all of the instructions, but the vast majority of them. You can see it's a pretty simple architecture to work with, obviously a lot easier than, current x86's 1,500 plus instructions. This is pretty clean and small. wanted to show you another demo using P-code for source sync analysis. So I was inspired by a Ghidra Infiltrate talk even a couple years ago by the Binary Ninja team and Sophia D'Antoine, where they used Binary Ninja and Binary Ninja's IL to identify calls to memcopy with potentially unsafe arguments. So I set out trying to build a similar demo to that, working with the P-code API, and ended up with something that's a little more complex, does some interprocedural analysis. It will drill down as well as go backwards. It will try to resolve what particular arguments are basically ending up in vulnerable function calls. I chose malloc as my call of interest. It's a simple call with a single parameter, and we all know the ways that malloc can go wrong. If a user-controlled value is allowed to get in there, maybe you malloc 0, or you have an integer overflow, for example. Lots of ways that this can go wrong. Now, I didn't want to go to the lengths of solving for literally every value passed to malloc. Obviously, that would require actually maybe emulating or running code or having a solver. In the general case, probably not computable. What I wanted to do was instead look if there were flows from interesting functions of note, potentially ones taking user input, where that input then flowed into malloc. Regardless of whether it was checked or not or manipulated, it would be interesting if I could audit all the places where a call to recv or a call to atoy or any of these other APIs results in an allocation being made. It's not very interesting to us if the size of malloc is always controlled. So using the P-code API, I was able to traverse through programs and find all those malloc sites, and then the arguments that go into them. So I'm going to scroll over to this malloc trace program. A lot more complex than the other scripts we've seen. This is about 800 lines of Java code that I've written. As you can see, using Ghidra's complex API, a lot of these functions take various objects, complex functions, many arguments. Something like Python, honestly, in my opinion, is not well suited for working in something like this, just because of all the types that you need. It's really great to get that compile time type safety when you found you're interacting with, say, a P-code op versus a P-code op AST object. So going through here, you see some handling for each type of P-code op, doing different things. If it's an indirect object, we're going to do a certain thing. Or multi-equal, these are sort of akin to phi nodes. If it's a negate object, we do this, or a negate P-code op, and so forth. And then some code going interprocedurally, tracing forward and backward in order to understand how parameters are passed to different functions. This script is not ready for public consumption yet, so I'm going to hold off on releasing this. This will be released probably in a week or so from now. It's not on the GitHub. All the other scripts I've shown today are. So let's go over to Ghidra and run the script. I prepared a demo binary for this purpose, so I'm going to import that. Closing our code browser. Looks like Ghidra crashed or something. Again, like Jeremy said, sometimes getting started with Ghidra can feel like opening up Visual Studios. You got to click through a couple dialogues, acknowledge some stuff. It's not just immediately popping up in front of you. So let's analyze this binary. So this is a pretty simple binary that I've prepared today. I have the source code over here. Basically, it's going to do a couple of calls to malloc with various controlled arguments, whether that's a simple value of 5, the return value of a function that returns 3, another function that calls yet another function, which can return a couple different things, and then also atoy, and then also does an allocation based on a parameter passed to this function itself. So we've ported it over here in Ghidra. I'm going to go to my scripting interface. Go down to Infiltrate, choose malloc trace, and now let's run this script. So the output is kind of ugly. Ideally, we would represent the kind of data flow as a graph. And Ghidra actually includes some code for what's called a graph provider, an API that lets you render arbitrary graphs. Binding Ninja actually does something as well included in Binja itself. The problem with Ghidra is that they didn't include the actual code for rendering these graphs with the release version of Ghidra. So you can construct graphs, but then you get an exception that says graph provider not implemented for this version of Ghidra. So someone obviously could go and implement this. There's lots of different ways you could do it. Maybe dump out some JSON and blow up a D3JS graph or OmniGraph, any number of these things. But right now, out of the box, Ghidra cannot easily visualize graphs. So I'm relying on some ugly ASCII output right now. But basically, as we go through this output, you'll see a bunch of debug information about how we're traversing these P-code operations all the way up to the top, where we look for a call to malloc. Can everyone see that? I'll make it a little bigger. So we find a call to malloc, or find malloc itself, find references to it that are unconditional calls, and then for each of those, we're going to step through and try to understand the particular var nodes that are passed into malloc, so kind of the abstract idea of a variable passed into malloc. How is that variable derived? And we can kind of crawl back through Ghidra, through the analysis the decompiler does, and figure out how those variables are derived. A lot has been made of Ghidra's P-code API, or P-code not being SSA, or single static assignment form. Out of the box, the raw P-code is not, but during decompiler analysis, it produces some SSA form modeling of some of the instructions. And basically, we can take advantage of the analysis the decompiler does in order to traverse through these graphs of variable definitions and data flow and so forth. I'd also add at that point, the decompiler is an external binary that runs and Ghidra talks to it over an IPC mechanism. It's actually written in native C++. So that is one barrier to running Ghidra on everything. It out of the box runs Linux, Mac, and Windows. But if you wanted to port it to, say, BSD, you'd have to make the decompiler run natively on your BSD system. So as we go through this, you can see we find, say, a constant value of 5 passed into malloc, a very simple case. But as we go further back, we can see cases where here we have to go through a number of operations and they ultimately resolve to a call to atoy. Scrolling further down, some more examples. We're able to find a case in this one where actually I'm mallocing the number of bytes that a recv call returns. You can see this over here. So we do recv and then pass the number of bytes the recv did and then allocate that number of bytes over here. In this case, we've interprocedurally traced backwards from the call site into the previous function. So we started at the analyze function, found a call from main to analyze fun, and then found that the value passed into analyze fun, the particular parameter there, was the source of that was a call to recv. And then here at the bottom, I have some more final output, which right now I'm visualizing as ASCII, but ideally in the future we would be able to visualize with, say, a graph provider, and kind of showing that call tree, where in this case, for this particular call to malloc, constant value of 5. For this one, we go down this function call tree to a call to the function return 3, which ultimately resolves to a constant value of 3. For this one, we go into get number 2, which then does atoy, but also we go to get number, and then get number can return one of several different variables, including 9, 0 or 1, or 11, or sorry, 9, atoy, or 11, as you can see here. And the last one, I don't have output for the interprocedural analysis where a parameter is passed, and I don't have pretty printing for that yet, so you just have to look at the ugly debug output up here. But I hope that gives you an idea of just how powerful Ghidra's APIs are and some of the P-code, and all the data flow is done for me automatically by Ghidra. All I have to do is kind of walk those trees of definitions. I don't have to worry about the particularities of architecture. I don't have to worry about stack versus heap versus global or register or anything like that. Ghidra tells me these are variables, and this variable was produced by adding these two other variables, and you can trace those back. And this variable came from an external parameter, so go trace to the third parameter to this function that was called, and so forth. It's very powerful, and I hope more people will look at it. And so, as I said, I'll release a blog post and the actual code for that once I clean it up, hopefully next week. A bit about SLAY. So we've talked through P code, which is the actual micro-operations, the unique IL that Ghidra uses. SLAY is Ghidra's language for describing instruction sets to facilitate RE. So SLAY serves two purposes. It both translates bit-encoded machine instructions, so a raw bit stream, into actual human-readable assembly instructions. And as well as doing that, it provides semantic information about what those instructions do that lets you lift them from raw instructions into P code. SLAY is based off of SLED, a 1997 academic IL called the Specification Language for Encoding and Decoding. So obviously SLAY is like a bigger, better SLED. Cristina Cifuentes was actually involved in the research on SLED, if that name sounds familiar to any of you. Her work is what inspired ILFAC of Hexrays and to build the Hexrays decompiler. So really seminal work in academia that inspired two major decompilers that, over 20 years ago got built up in different ways, kind of in parallel. So some examples of how SLAY works. Let's look at a simple instruction, jump to a 8-bit address, jump to a single byte, basically. In this case, concretely, we'll look at jump to +5. And you'll see here the listing display of the operation. We have the hex values over there, and then the actual P code here at the bottom. So let's see how this is composed via SLAY. So here we have the definition for x86 and the SLAY spec file. This is all included. You can just pull these up and read them. Here we specify the actual mnemonic value itself, JMP, followed by the relative 8-bit address. And then you'll see over here, we say equals byte EB, followed by rel8. So they're specifying concretely this instruction must have the byte EB. And it's going to be followed by the relative address we're going to jump to. And then here in the brackets, we specify the semantics of the code. Go to rel8. Go to that address that's specified. Here's some additional definitions of how rel8 is formed. And it basically says this is in particular an address in RAM and relative by the number of the native size of the architecture and so forth. And we can see how this translates out into the actual listing view, where the raw bytes are translated there. We see the P code here is constructed from the go to rel8, and then also the mnemonics and everything else. Another example, XOR AL with an 8-bit value, so a single byte. This one is always going to be 34, and then followed by the 8-bit immediate we're going to XOR with. This is a little more complex. We translate from a single x86 instruction into 5 P code ops, and these are highlighted here. So let's look at the SLAY definition for that. In this case, we have concretely, it needs to say XOR, that's the mnemonic for XOR, and then AL, followed by the 8-bit value, the single byte that we're XORing with. And always the first byte is going to be byte 34, followed by the mask for AL ANDed with the byte. In that case, the mask is 0, so it's just going to be that single byte. And then we see two macros here, logical flags, result flags, and then we also see that AL is equal to AL XORed with the immediate 8-bit value. So bringing those macros into view here, we see the results flag macro and the logical flags macro. So for this instruction, the CF and the OF, the overflow flag, are always set to 0. And then the SF and ZF, the 0 flag, are going to be dependent on the results of this XOR. So putting it all together, we see here the actual bytes of the instruction. Then we see the opcodes themselves, XOR, AL, 57. And then looking at the P code, we see that the logical flags operations, setting these two flags to 0, is right there. We then see that AL is XOR of AL with 57. And then we see the results flags. So based on how the comparison went, we'll set the flags accordingly there. One final one, unique kind of architecture-specific instruction, RDTSC. This basically queries the CPU time counter and sets values accordingly. This instruction does not take any parameters. It's just always OF31. So we can see it here. And we'll see the SLAY spec. It says it's always byte OF and then byte 31. So there's no arguments or anything. It's just if you see OF31, you know that it's RDTSC. But here it's specifying the semantics. We say that this temporary value of 8 byte width is result of RDTSC, and then EDX and EAX are two kind of subslices of that temporary value. Now, RDTSC is then defined as a user-defined operation. Basically, it's kind of an intrinsic. The P code is saying we don't have a way of modeling this instruction. Obviously, a user could come in and provide that modeling. If they were doing program analysis or something, they might say model RDTSC in this way. But basically, for now, it's just kind of a dummy value. It'll just return an arbitrary, clobber these 8 bytes. So then looking at the P code that's constructed here, we're going to put out the hex values, put out the opcode itself, RDTSC, and then we're going to say that this temporary value is the result of calling RDTSC, this kind of intrinsic value. And then we take the temporary value, the U9C60, and then we take 2 sub-pieces of it, 2 slices of it, and put those into those registers there, as you can see. So that concludes our discussion of P-code, SLAY, scripting, interactive use of Ghidra. Moving into the conclusion, I want to talk through some discussion points. First off, other major features of Ghidra. We've only here covered a brief subset of what Ghidra can do. It can do a whole lot. Multi-user collaboration built into Ghidra. First-class native feature. So I'm sure many of you have seen all these IDA plugins over the years that enable you to do IDA collaboration. Built into Ghidra, first class, there's a Ghidra collaboration server and sort of a Git push-pull model. Version tracking built in, so not as good as bindiff, but you can basically diff between versions of a program, particularly if you have a Ghidra database that's well annotated. You put a lot of comments and names in there. Very easy to port them to the next update of that program. It's easily extensible for new programs, new architectures, new binary formats. Headless mode processing, as I briefly showed you. Really nice integration with Eclipse. You can debug all of Ghidra natively from within Eclipse as you work on it. At RSA, Rob Joyce promised a debugger would be forthcoming, so hopefully that'll be out there. And complementary to the debugger, there is an undocumented P-code emulator inside of Ghidra. There's no code to drive it right now, but there is actual emulator code. So if you wrote code against the emulator bindings, you could emulate P-code and actually emulate default functions and things. It's obviously not going to be as fast as running natively and so forth, but you can imagine with obscure architectures or for things like symbolic execution, this could be a useful feature. Another thing, a lot of people ask me to compare IDA versus Binary Ninja versus Ghidra. Honestly, I'm a huge fan of all 3 of them. I just took the Binary Ninja training, big fan of that. I've been using IDA for years, more recently I've been playing with Ghidra, and they're all great for different reasons, and I don't think one is better than any other. But I wanted to highlight some of the unique features of each. Obviously, IDA and Ghidra are both very mature as software. They both have, it seems like 20 plus years of development behind them. So they're very mature, they're well tested, they support a whole lot of stuff, but they're also kind of brittle, they're not going to change a lot. They're not cutting edge and under active development like Binary Ninja is, which is really great to see. Every day you get new updates with Binja and new features being added. 2 major points, IDA and Ghidra both have amazing decompilers. Obviously, Binary Ninja is working on one. IDA has a great corpus of existing plugins. Ghidra has very little in the way of community plugins. There obviously has been a lot of excitement around Ghidra and a lot of GitHub projects popping up here and there, but not as well supported as the corpus of plugins available for IDA. I'd also note Binary Ninja has a number of plugins, and I'm understanding there's a forthcoming UI view for integrating new plugins from the community. That's going to be really great. I'd also highlight, obviously IDA and Binja both offer paid support for customers. You can't pay NSA for Ghidra. Binja also has a really awesome community. If you go on the Binja Slack, people always collaborating, sharing information, talking. That's really unique to that tool. And now on the other side, you can't pay NSA for Ghidra because it's free. It's available here on GitHub. And it does seem like the agency has been supporting the tool since its release. A couple hundred GitHub issues, a lot of them have been addressed by the agency, official responses. We'll add this feature, we'll take pull requests and so forth. People also ask all the time about the decompiler. So Hexray's decompiler is kind of an optional add-on to the tool, whereas Ghidra's is deeply integrated with Ghidra. Similar architectures where they're using an IL. In IDA's case, it's microcode, and Ghidra's it's P-code. What's really nice and unique about Ghidra, and we didn't get a chance to show today, is that Ghidra's compiler supports any architecture that it can disassemble, it can decompile. So any architecture you write a P-code spec for, or a SLAY spec rather, you get automatic decompiler integration. So there are whole architectures that no one's really been ever able to build a decompiler for that out of the box Ghidra supports. And it also means you can easily extend Ghidra with your own custom architecture plugins and kind of get for free that decompilation. If you just write the spec that translates from these instructions into P-code, the decompilation comes along with it. IDA has all the Windows type libraries built in, which is a really great feature if you're looking at Windows apps, particularly, say, malware analysis. It's great to know all these different structure definitions. Ghidra doesn't have that yet. There actually is an alternate project that includes some of those definitions, but out of the box, not well supported. I'd also note, I think Ghidra's decompiler produces more idiomatic C, less go-to statements, less do-whiles. So it looks more like C you can run. It looks more compilable. I've even heard people have copied and pasted and direct straight up compiled Ghidra decompiler output. But on the downside, it's a little less interactive than IDA's decompiler. In IDA's decompiler, you can map variables, you can change representations from hex to bytes to strings and so forth. In Ghidra, you have to go to the listing view and change those. I'd also note a big feature everyone plays with Ghidra out of the box, and they say, I'm clicking variables, why am I getting highlights? You need the middle click. So if you have a mouse with a scroll wheel, you click on the scroll wheel itself to highlight a variable. Obviously, that's configurable, but if you're on a laptop, it's not going to work out of the box. So I have to highlight that for everyone. Another comparison to be done, ILs. So Binary Ninja has this multi-level IL with the LLIL, the MLL, and the forthcoming high-level IL. Binge's IL is designed to be machine consumable, but also human readable, and it provides native out-of-the-box SSA form. Ghidra, on the other hand, has P-code. It's a single-level translation, just instructions to P-code. During decompiler analysis, it gets enhanced. Some instructions are inserted, some things can be changed, parameters will be associated with different instructions, and there will be an SSA form constructed, but it's certainly not as clear and concise a delineation from different levels of analyses the way Binary Ninja does it. It's also designed for machine consumption first and not human readability. That said, it is more readable than a number of other ILs, but it's certainly not as nice to look at. A unique feature of Binary Ninja that makes it so readable is the use of deferred flags. So whereas Ghidra will show you explicitly every flag it calculates, Binary Ninja will defer those calculations until they're actually used. So if they don't need to calculate or use a particular flag, they won't show it to you. So visually showing you a single basic block in Binary Ninja's LLIL, MLIL, and then in Ghidra's P-code. Obviously, Binary Ninja is a lot more readable. Ghidra's very verbose on the other hand, and less readable. And then you can see here at the MLIL, you actually, you don't have a call instruction, you actually have a call to scanf. Wanted to highlight some uses we like using Ghidra for. Scripting is awesome, as I showed you. Firmware analysis is great. Today we focused on traditional desktop architectures, x86, but it's really a game changer looking at decompiling, say, firmwares or obscure architectures. I was recently looking at a big VxWorks binary, about 11 megabytes, something like 22,000 functions. Ghidra found 3,000 more functions than IDA did, and also let me decompile big endian MIPS code. It was a game changer. I'm not an expert at MIPS big endian, and to be able to out of the box look at this pseudo C and work with that was fantastic. Analysis of software that hexarrays can't decompile is also great. As I said, the MIPS big endian is one example. It's great for collaborative, long-term professional RE. Like I said, it feels kind of like Visual Studio's. Heavyweight, slow to get started, but if you're working with it in a professional environment, it's the real deal. It's the great tool. And I'd also note Ghidra is really great for professional reversing at a computer workstation. So don't see too many laptops open here today, but if you were on a laptop, it's not the best experience. It's much better sitting at home, 2 or 3 monitors, a full keyboard with function keys, a mouse with a scroll wheel and a middle click. It really feels like it's designed to be worked on a professional, workstation environment. One last thing, an opinion, Java versus Python. I showed you the Java and the Python APIs, and I know a lot of people don't like Java. It's not the coolest hip language anymore. Python is a lot cooler. I do think Java is better for working with Ghidra. In particular, that's because of Java's type safety, that if you try to compare, say, a P-code op AST object versus a P-code op, or an address iterator object versus an address, you'll get a compile time exception. With Python, you get a runtime exception. And because Ghidra's API is natively implemented in Java, the Python binder is simply a kind of a layer of abstraction with the Jython over the Java, but it really feels like you're writing Java code and Java function calls kind of bound together with Python control flow. So you get to do the for-ins, you get the nice string repers, you get all the constructs of Java, but ultimately you're just calling into constructs of Python. Ultimately, you're just calling into underlying Java code and working with Java objects that are kind of brittle. I do like the Python for rapid prototyping, using the included console to play with objects, see what parameters they have, and so forth. It is well documented. You can do help, you can do dir, and so forth. But for production scripting, particularly longer form scripting like the P code, the program analysis I showed you, strongly recommend going with Java. Finally, I wanted to highlight a number of features in Ghidra. I'm not going to read these all to you, but you can really tell this tool was built for reverse engineers by reverse engineers. So many little ergonomic things that just, you want to import a piece of malware from a zip file. You can just drag it in and it'll open the zip file for you and import from it. Processor manuals built in. Any instruction you're looking at, you can right-click, open processor manual. It has integration. It knows the manual, the PDFs, and what page the instructions are on. So it'll take you to the page 6,000 of the Intel manual where this unique instruction you're looking at is documented. The snapshot viewer is great. The project-based ability to do multi-binary RE. There's unique windows like a checksum generator. You can highlight a region of memory and get a checksum of that region of memory. You can imagine being a malware analyst. You might highlight a piece of memory and want to see a checksum if you're looking for a signature or something like that. All of this built into Ghidra, no plugins, no additions. This is first-class official features of the tool. In terms of contributing to Ghidra, the code is available on GitHub under Apache License v2, and you can check out NSA's official website for the tool. There have been a number of Twitter accounts and things that have come up that are kind of unofficial. As far as I can tell, the only official resource is GitHub/National Security Agency and also GitHub or GhidraSRE.org. And the agency, in the 2 months since the tool has been released, has already released 2 minor updates. So they do seem to be maintaining this tool, responding to community questions and pull requests and things like that on GitHub. So that just about wraps us up. We're going to go to the conclusion, and want to say Ghidra is a really awesome tool. We've included links to our demo material. Hope you'll check that out, and do look out for that P-code blog post next week. Some big thank yous to NSA's Ghidra team. As we said, Jeremy and I are here as private civilians, big fans of the tool. Never contributed code to Ghidra, so all the credit goes to the team that built this. Also to Rob Joyce for facilitating the release at RSA this year. We want to thank Rolf Rolls, Evan Jensen, and Sophia Dantoine for their insights, particularly into Ghidra scripting and into program analysis and SSA form and things like that. They've been invaluable helping us understand those concepts. And a big thank you to Dave Eitel and the whole Infiltrate team for hosting us. Jeremy, you want to say anything?
Yeah, I guess one last thing. If you really liked Ghidra or you really want to dive in and you don't want to go it alone, I'm doing some training alongside Black Hat. So there's a new conference called Ring Zero, and it's just for trainers, and it's got Bruce Dang, Alexei, a number of other great names. And so I'm on there too, and I'm doing a 4-day training on Ghidra at Black Hat. So if you want to get past just clicking the menus or running other people's scripts, then that would be a good place to start.
Great.
So
thank you so much.
Thank you.